Good morning. So in this video we are going to, is it okay? Yeah. So let's start to discuss about analytic function, and you are well known about the definition and some of the properties. So in this lecture I will recall those. You may take it as a remedial class. Okay. So what is analytic function? You can relate with differentiability. Uh, if a function is differentiable at a point, and it's every point in its neighborhood, so you can find at least one neighborhood where the function is differentiable. So this is the concept, and suppose this is the point A, and uh, at least we have a neighborhood where the function f of z is differentiable. Now what does it mean? So let's start to find out something which is related to analytic function. Okay. Suppose if dash z exists. Now it implies that, so limit, z equal to x plus iy, so we can write here del x comma del y tends to 0 comma 0, and if dash z means and you have u plus iv, so you can write for the real part, what is that, the difference, that is x plus del x, y plus del y minus u x comma y divided by del z, that means del x plus I del y, and plus I into v of x plus del x, y plus del y minus v of x comma y divided by del x plus I del y. Now as the function exists, that means differentiable, so the limit exists, and in that case whatever the line of limit, if we approach the limit from this line del x comma 0, that means putting del y equal to 0 in this function, we have some result. So let's find first, and if you put del y equal to 0, so this part will be vanished, sorry, so this part will be vanished, and this part will be vanished, similarly this part will be vanished. So what is remaining here, u x plus del x comma y minus u xy divided by del x, so which is nothing but ux, and for this function if you put del y equal to 0, that means this is also vx, is not it? Now if you put the limit from this line 0 comma del y, so in that case you have del x 0, this part is 0, and this part is 0, this part is 0. So here we have I will be present there, so in that case u x comma y plus del y minus u xy divided by I del y, so it will be like 1 by I into u of y, and similarly here, so I will be vanished, and v of y. Now from the property of limit, it is well known that whatever the line of approach to that limit, from this line or this line or this line, the limiting value will be same. So in that case, the imaginary part, if you simplify this, so uy plus vy, so real part will be equal to real part, that means ux equal to vy, and from this line uy will be equal to minus vx, and these two equations are called Cauchy-Riemann equation, and it is very important regarding analytic function, and we will use these relations in many problems. So what is the conclusion? Conclusion is that if a function is analytic, then Cauchy-Riemann equation will satisfy, but I have not proved yet the reverse, so reverse may or may not be true. So give an example of analytic function or a function which is not analytic. Okay. Now, so analytic function f of z, if you take f of z equal to z bar, so f dash z equals to limit del z tends to 0 f of z plus del z. Oh, I'm changing the pen. My god, where is my black pen? Okay, so let's start with blue green. Z plus del z minus f of z divided by del z. So in that case, limit del z tends to 0, z plus del z means z bar plus del z bar, so you can separate it, and minus z bar divided by del z. In that case, limit del z tends to 0, del z bar divided by del z, and here we have the limit, and it is 1 if you approach the limit for del x comma 0, and will be minus 1 if you approach the limit from the line 0 comma del y. That means the limit is not unique, and hence the function is not analytic. Also, we can conclude that if Cauchy-Riemann equations are not satisfied or not hold, then definitely the function is not analytic. Okay, now you can find the polar equations of Cauchy-Riemann equations also. I'm just giving hints, and you can solve it as a task. So ux equal to vy and uy equal to minus vx. These are the Cauchy-Riemann equation. And what are the relation between x and y? X equal to r cos theta and y equal to r sin theta. So in that case, you have to find some relation with u theta or v theta, vr v theta, like this. We have to find some relation among them. Okay. Sorry. This is now let's start with okay, del u by del r. We have to find the relation among these. So del u by del r will be equal to del u by del x into del x by del r, as u are the function of x and y. So using chain rule, we can write this, and plus of del u by del y into del y by del r. So in that case, we will find del x by del r from this. So ux cos theta plus del u by del y that means uy into sine theta. That's it. And similarly for del u by del theta, you will find some result, and del u by del theta, that means del u by, so you can write directly del u by del theta, that means similar approach ux, and del theta means minus r sine theta, and similarly here uy into r cos theta, and del v by del r, del v by del r, so similar approach vx cos theta plus vy sine theta, and del v by del theta will be so vx minus r sine theta, and del v by del theta, so vy into this approach, vy into r cos theta. Now you can use those relations. Put ux equal to vy here, ux equal to vy, your v theta, ux equal to vy, this function is vx, r sine theta, so yeah, ux equal to vy. If you put ux equal to vy in that result, so first use it different frame. So in that case, ux, if you put here ux equal to vy, so vy cos theta, and uy equal to minus vx sine theta. So you can equate them, vy cos theta r multiplied and minus vx sine theta r multiplied. So if you multiply r here, so r ur will be equal to v theta, is not it? Similarly, from these two equation, ux equal to vy, ux equal to vy, if you put here minus r sine theta, and uy equal to minus vx r cos theta. Now take vx cos theta, and vy sine theta, and then negation. So you can write here u theta is multiplied by, so if you put minus r, if you multiply minus r here, minus r vr, then the result will be same, is not it? So the result is u theta plus r vr equal to 0. Check this calculation, I think you will find it. And u theta, and so we have the relation between ur and u theta and vr. So it's okay, I think you can check it. Now we have to learn some different relations of analytic functions. And what are these? In that case, okay, let's start cauchy integral theorem. Or before that, we have to take some knowledge on singularity. Okay, 2 minutes for singularity. Singularity where the function is not analytic. Suppose fz equal to 1 by z. Now z not equals to 0 For z equal to 0, the function is not analytic. Sin z by z, the function is, for if you take limit z tends to 0. What about this? So at z equal to 0, is the function analytic? Take or simpler example, z cube minus 1 by z minus 1. So in that case, is the function analytic at z equal to 1? What do you think? Now take another function, sine 1 by z. What about this? Take cosec 1 by z. What about this? So are this function analytic? No, it is not analytic. But what about the singularity? That means the nature of singularity, are they same? So we are going to investigate here. So let's start with this function here. Easier. In this format, if you put z equal to 1, it is not analytic, but we can remove the singularity if we calculate, and you know this will be like a polynomial function, so it is analytic. So in this form, the function is analytic. That means z equal to 1 is a removable singularity for this function. Clear? Similarly, sin z by z, if you take limit, the limiting value is 1 finite, and that is another theorem, the function is removable singularity or not. But simply you can take sorry, oh, it's not working. What is this? So sin z, just take sin 1 by z into z minus z cube by factorial 3 plus z to the power 5 by factorial 5 and so on. And if you simplify this, so z square by factorial 3 plus z to the power 4 by factorial 5 and so on. So nothing to equate with 0 in denominator. That means there is no term involving negative powers of z. That means the function is analytic. And thus these two functions, function 1 and function 2, are removable singularity at, for this function at z equal to 0, and for this function at z equal to 1. Now what about this? Here also we can say that at z equal to 0, the function is not analytic, but it is not a removable at all. And what about this? This you can write it as sine 1 by z, and I have already mentioned you in classes. So just put sine 1 by z equal to 0. From there you will find 1 by z equal to n pi and z equal to 1 by n pi. So these are the singularities. If you put n equal to 1, that is at 1 by pi, at 1 by 2 pi, 1 by 3 pi, these are the singularities. But when you tending to n tends to infinity, you will find the values of z, and in neighborhood of 0, if you put n equal to infinite here, so z will be 0. But in neighborhood of 0, you will find more singularities. You can't separate these singularities, and it is a special kind of singularity. It may be called as non-isolated. So I have mentioned another term, non-isolated singularity. Now I am giving the summary of all these singularities in a format, and after that I will go to cauchy integral formula. So whatever I mentioned, if you took at singularity, you can divide as isolated, isolated, and here non-isolated. Here from isolated you can put as removable. Pole means a finite word. I will give an example for this. And essential singularity. And for non-isolated singularity I have given that example. So removable I have mentioned, that is sin z by z at z equal to 0. And if you take here pole, that means take that same example with z to the power 5. So you will have, if you simplify that, so first term is z, that means 1 by z to the power 4, and minus second term is z cube, that means 1 by factorial 3 into z, and the next term will be positive, that is z to the power 5, so 1 by factorial 5 and plus z to the 7, so z square by factorial 7, and so on. So these two terms, this involves z and this involves z to the power 4. So actually this function is not analytic for z equal to 0 due to these two terms, and in that case we will say the function has a singularity or pole of order 4. So pole of order 4, you can just recall that series. If you write f of z equal to sum of a n, you can write as z minus z0 whole to the power n plus sum of bn divided by z minus z0 whole to the power m. So if bm not equal to 0 and bm plus 1 equal to 0 equal to bm plus 2 and equal to 0 and so on, then z equal to 0 will be pole of order m, as we have the highest term which is non-zero is bm. So this is pole, and essential singularity you can take that example sin 1 by z. So it is not pole and removable singularity, is not it? If you express that is 1 by z, 1 plus 1 by z plus 1 by z square by factorial 2 and so on, so it will not be finite. For this case pole is finite and essential singularity is not finite, so it is not removable singularity and not pole. And non-isolated I have already mentioned it, that you can take 1 by sin 1 by z like this. So if you equate this to 0, and you will find z equal to 1 by pi, 1 by 2 pi, 1 by 3 pi and so on. So in that case you can't separate the singularities near to 0. So if you take singularity near to 0, you will find another singularity within the neighborhood. So these are the simple some points you have to remember. Obviously you will read the books, but here this lecture will remember you what to read and the concepts. If you want to know more, then you can contact me in classes or in WhatsApp. So let's start with another topic, Cauchy integral formula, Cauchy theorem. What is Cauchy theorem? Okay, in that case, so suppose this is a closed contour, you mean just take it as closed curve, and the function f of z dz will be equal to 0 as per Cauchy theorem. So how it is possible that if the function is analytic on a closed contour, closed curve C, then the function is analytic. Actually, the Cauchy applied this theorem. Cauchy started, but he mentioned two property. Number one is f of z will be analytic, and second thing is f dash z will be continuous. So these 2 points are there. So let's start to prove the Cauchy theorem. Just take integration f of z dz equal to u plus iv and dz equal to dx plus idy over c. So c u dx minus v dy and plus I of v dx plus u dy. Okay, now we have to use Green's theorem to find the Cauchy-Riemann equation. And what are these Cauchy-Riemann equations? Ux equal to vy and uy equal to minus vx, the partial differentiation of u and v with respect to x and y. And here the format is different. As the function f of z is analytic, Cauchy-Riemann equation will be satisfied, and also in Cauchy theorem it is mentioned the function is differentiable and the derivative of f of z will be continuous throughout the region, throughout the closed curve. So we can use Green's theorem. And what is Green's theorem? M dx plus n dy will be equal to del n by del x minus del m by del y into dx dy, and it is surface integral. So you can use the same technique and use the Cauchy-Riemann equation. We will find that this will be 0. So let's start, and this is m and n. So minus del v by del x minus del u by del y into dx dy for this function, and I into integration over s, put it as surface here, and del u by del x minus del v by del y into dx dy, and ux equal to vy here, ux equal to vy, so this part will be vanished if we put ux equal to vy, and here ui equal to minus vx, so this part will also be vanished, so will be equal to 0. So what is Cauchy theorem? If the function is analytic on a closed curve C and the derivative of f of z, that is the function, is continuous, then we can use Green's theorem and we can use Cauchy-Riemann equation, so the value will be 0. So it is very fantastic result, and you will find it is important in several problems, several related theorems. Now what are the extensions of this Cauchy-Gaussian theorem, which relaxes the second condition, that continuity of f of z is not required, and he also proved it. So simply, if the function is analytic on a closed curve, the value will be 0, integration will be 0. Okay, so this is our result. Now Cauchy, from this result we can find another result, Cauchy integral formula, and before that we have to prove a result that if we have a curve C and within this curve suppose we have another curve C1, Cauchy theorem says the integration value will be same, will be equal to dz if it is over C1, so integral value will be same. How it is possible? So I am giving a small proof for this. Okay, just take a pipeline here. Just put it here and put it here. Okay. Now, take this line. Take this line, anti-clockwise line. Okay, and give some name here. So C, but if you start here, A, B, okay, C, D, F, E, okay, G, H, A. So from this line we can use this total curve as it is closed. If you start here, the curve is closed. We can use Cauchy theorem here. That means we can write here from this curve. You can write the outer curve first. So A, B, AV and C. AV C integration over this f of z dz plus this part, that is CDF f of z dz, and plus this small curve, that is GEF f of z dz plus integration over FDC f of z dz will be 0, as the function is analytic as mentioned, and on a closed curve, so the value will be 0. Now if you take this, so ABC, that means whole curve, and you can put it as C here, f of z dz. If you take this pipe very small, then the result will be the total curve. And for this CDF, this line, and CDF and GHA, CDF and GEF, this is, and FDC, sorry. So CDF and FDC, CDF and sorry, it will be actually GHA. So these two part will be equal. Integration over this line and integration over this line will be same, but the direction is different. You can check here. So this direction is in that line and this direction is in that way. So it is very obvious, this part will be vanished. So this part will be vanished. Now we have ultimately this part GEF. This is a smaller circle, smaller closed curve. If you take this line very small, that is this pipeline is very small, then we can write GEF as minus C1. Why? The direction of this curve is clockwise and direction of this outer curve is anti-clockwise. So it is C, but if you want to put FEG, this is clockwise direction, and if you put it as C1, then you have to write minus of C1 f of z dz. Check it, you will understand, very easy thing. And so what is the result? Result is integration over C f of z dz will be equal to integration over f of z dz C1. So this is very important result to prove Cauchy integral theorem. So let's start Cauchy integral formula. So Cauchy integral formula says if a function is analytic, that is f of z is analytic, and analytic at a point, that means you will find a neighborhood of a where the function is differentiable. Now cauchy integral formula says f of a will be equal to like this 1 by 2 pi I integration f of z by z minus a, and its extended form will be like this factorial n by 2 pi I and integration over f of z by z minus a whole to the power n minus 1. So we have to prove here. Okay, let's start. This function, if you take this closed contour C and take a point here A, just take a circle, taking A as center, and take the radius as small as possible, r. Now we can write that integration f of z by z minus a dz, sorry, over C will be equal to integration over C1, because we have excluded that part z minus a. Total integrand is not analytic at a, and we have excluded that part, and we have this region. So this integrand is analytic within this region, is not it? So we can use Cauchy theorem here, and what Cauchy theorem says, the integration over the outer curve will be equal to integration over the inner curve, whatever we have proved just now. Now if you take this as circle, now it is very important to write mod of z minus a equal to r. This is the equation of circle. From there you can write z minus a equal to r e power I theta and z equal to a plus r e power I theta. So just put this z and dz equal to will be I r e power I theta. If you put it here, you will find a result which will be equal to the result written in this green line. So just take and theta equal to 0 to 2 pi, f of z will be equal to z equal to a plus r I theta, and d theta, sorry, d theta you can write dz equal to I r e power I theta, and d theta divided by z minus a equal to r e power I theta. So r e power I theta is vanished, I is there, and if r is very small, we have already mentioned the radius is very small, you can take it as infinitesimal small and put it as 0, so this part will be vanished. So in that case f of a will be outside of the integration I into f of a, and there will be only d theta, so you can write it as 2 pi, so 2 pi I into f of a. So this integration value is equal to 2 pi I f of a. So f of a will be equal to 1 by 2 pi I integration over c f of z by z minus a. Now if you take successive derivative, if you take successive derivative on this line over a, you will find this result, f for n a, f factorial n, like this, and you will try in home. I think you can solve it. Now I am giving two more examples on this Cauchy formula. First one you can, okay, So just take a circle, and this is 1 and this is -1, and okay, so okay, consider a function f of z equal to z to the power 5 plus 4z. Polynomial function, it will be analytic, and take z square minus 1. Okay, z square minus 1. So I'm changing the circle. If you change the circle, to exclude one point, so just take this kind of circle. So what is that circle? Radius 1, center 1. That means we have to integrate f of z over c, and c is like z minus 1, 1 center will be equal to 1, radius 1. So what is the integration value here? A very interesting problem. If you check, there are two singularities, z square minus 1 equal to 0 and z equal to plus minus 1. So plus 1 it is within the contour and minus 1 it is outside the contour. So if you want to split it, you can write z square minus 1, z minus 1 by z plus 1. So z plus 1 minus 1 by z minus 1. In that case minus will be there, so better take z minus 1 into here. Now it will be z plus 1 minus z plus 1, so 1 by 2 into f of z, whatever it is there, z to the power 5 plus 4z, and this is the integration. This integration becomes this. Now we have the two parts. One is I1. If you take this as I1, so integration over c, and 1 by z minus 1. So 1 by, that means z to the power 5 plus 4z by z minus 1 into dz. So this is I1, and for this part you can relate that cauchy integral formula. This is f of z and z minus a, so it will be equal to 2 pi I into f of a. So f of 1. Is it okay? So f of 1 means 1 plus 4, that is 5, so 10 pi I. This is the result of the first part, and you can take I2 as this part. So I2 is what is I2? Z minus 1 we have taken, now Z plus 2. Actually in I2 it is we have 1 by 2 multiplied with this. So in that case I2 will be like this, and 2, so result will be 5 pi I. Now for the second part, what about this? Z equal to minus 1, it is outside the contour, this is minus 1. So you can just simply put it as 0, because the function z integration half z5 plus 4z by z plus 1, it is minus there, this part will be equal to 0, because this function is fully analytic within this domain, this region. So only the result will be 5 pi I. Check it from yourself. And okay, we can use also the extended formula. If you take it any function, like for example, you have to find e power z by z cube. z cube. And over the curve can be written as mod z equal to 1, mod z equal to 1. So you can use this as this function can be written, that is e to power z will be there, and z minus 0, so z minus 0 whole power 2 plus 1. So you can take it as n equal to 2, and so this part will be equal to f double dash n, f double dash as n equal to 2 here, 0 into 2 pi I by factorial 2. So you can solve it. So similarly we can solve many problems on cauchy integral complex integration. So this lecture will only give you some idea and some related notions, so you can use it in your problem solving. Thank you very much. Bye.